So at this point, we've done a fair amount of math, right? We sort of went through this example of starting with the potential energy and going from the potential energy to figure out what the force is by taking partial derivatives of the potential energy. We've shown that that seems to work. In this video, I actually want to sort of put this in a bigger picture context, because it actually is a really helpful idea for sort of understanding some stuff about the way the world works. And so in some ways you might think about this as why everything in the world looks like a spring. So why does the world look like a spring? Okay, and you might wonder what I mean by why does the world look like a spring? Well, one way to say what I mean by why does the world look like a spring is, why is it that pretty much any force, if you're close to equilibrium, looks a lot like a spring force? And the answer really has to do with this idea that force has to do with potential energy, and thinking a little bit more about what that might imply mathematically. So let's sort of think about some properties that potential energy must have for systems that are at equilibrium. So we're going to look at a system that's at equilibrium. And when I say at equilibrium, what I actually mean is if you displace the system a little bit from that configuration, it will actually go back to that configuration. So if you imagine a sort of a bowl with a marble in it, the bottom of the bowl is the equilibrium point. If I displace a marble a little bit away from the bottom and let it go, it will go back to that equilibrium point. So that's the sort of position that it wants to return to. So if we think about potential energy at equilibrium, potential energy at equilibrium must be at a minimum. Right? Potential energy has to actually be minimum. Potential energy has to be at a minimum at equilibrium. In particular, what we actually need at equilibrium is that the partial of the potential energy with respect to x, and the partial of the potential energy with respect to y, and the partial of the potential energy with respect to z, that all of these things are zero. Right? Because if they weren't zero, if they are not zero, that actually implies that there's a force, right? And if there's a force, you're not at equilibrium, right? So if, in fact, you're at rest, right? If the system is at rest, if it's at a resting point, that means that there's no net force acting on the objects, right? They're not accelerating. And if there's no net force acting on the objects, that in turn must mean that the potential energy actually has to be at a minimum. So if you think about some common examples of that, we could think about, for example, the sort of mass on a spring, right? So if this is my resting point, right, and if I actually ask the question, what does my potential energy look like as a function of position, right? Well, my potential energy looks like 1/2 kx squared, right? It looks like this, right? And the potential energy is a minimum at that resting point, right? And if I displace the system a little bit to the right, the partial of the potential energy with respect to x is positive at this point, which gives me a force that is in the negative direction, right? If I just displace a little bit to the left, the partial of the potential energy with respect to x is less than 0 at that point, which gives me a positive force, right? So when I displace a little bit to the left or a little bit to the right, the object wants to return to that equilibrium point. Okay? And that's what actually makes it be an equilibrium point, is the idea that the potential energy is at a minimum at that point. Okay? I can also take this spring a little bit further and ask the question, well, what does this mean about the force? Well, since the force is minus the partial with respect to x, right, the force actually looks like this. Boy, and I suck at drawing. That's the origin point. Right, the force, which is minus the partial with respect to x, right, is 0 at the equilibrium point, right? It's positive when I'm below the equilibrium point, and it's negative when I'm above the equilibrium point. Okay? So a big idea number one is, when you are at equilibrium, potential energy is minimized. Okay? So the second part of this is thinking about what the properties of a function are when you're close to equilibrium or close to a minimum. Function. So let's imagine I have some potential energy, and I'm going to just draw it in one dimension, but you certainly could think about this in multiple dimensions. Right? So here's what my potential energy looks like. It's some more complex shape. One question I might ask initially is how many equilibria are there for this system? And there actually are two, right? I could imagine this being an equilibrium, right? If I thought about putting a marble right here, it would sit there. Similarly, if I thought about putting a marble right here, it would also sit there. Although this marble, pretty clearly, if I displaced it enough, it would actually fall down into this minimum. So there are actually two equilibrium points here because there are two local minima for this potential. Let's think about what the forces are near to the equilibrium. Well, my force, right, is going to be given by minus the partial with respect, in this case, let's say this is x, the partial of the potential with respect to x in the I hat direction. Okay, well, how could I think about this function near equilibrium? Well, it's got a minimum there, and since I'm near equilibrium, let's actually do an expansion. So we're going to use the Taylor series and expand about this point. So if I call this point my x EQ, right? Then I would say my potential at some point x, right? X is close to x EQ is going to be what? Well, the first approximation, if I'm expanding this function, would be to say it's approximately the value of the potential at x equilibrium, right? And my next term in the expansion is going to be to say, well, I could do a little bit better than just saying it's that the value a little bit away from x equilibrium is the same. Maybe I could take the slope of the function into account. So I could say it's actually that plus the partial of the function with respect to x, evaluated x EQ times x minus x EQ, right? And I could go a little bit further and say, okay, well, the next term is going to be a term that has to do with the sort of curvature at that point. So I'll get 1/2 partial with respect to x squared. So the second derivative with respect to x, again, evaluated x EQ times x minus x EQ quantity squared, right? And so on, right? So I could do a Taylor expansion around this point in order to figure out what the potential was. And since I'm going to be close to that point, pretty clearly as I go to higher and higher order terms, those terms are not going to be very important because this value, this quantity x minus x EQ is going to be small, and so x minus x EQ cubed and x minus x EQ x equilibrium to the fifth power, those things are going to be pretty small. So probably I'd do pretty well approximating my potential if I just kept the first few terms. Okay? Well, what does that mean that the force? So let's think about this a little bit now with respect to what happens to this function when I'm at equilibrium. Well, this clearly is going to be some value. But what's going on with this? This is the partial of the potential with respect to x at the equilibrium point. And the partial of the potential with respect to x at the equilibrium point is by definition 0. Right? So this term is 0. In fact, this term has to be 0 because that's what makes it an equilibrium point, right? The derivative with respect to position is 0. The bottom of this thing is flat. It's a minimum, right? So the first term that actually sort of gives me any information in this is this term, right? So I would actually say the potential at x is approximately the potential at the equilibrium point plus 1/2 second derivative of the potential with respect to x squared evaluated at the equilibrium point times x minus x EQ squared. Okay? And this is going to be a reasonable approximation for pretty much any potential, as long as it has a second derivative, and as long as I'm close to the equilibrium point. I mean, clearly there are cases you can think of where this would be a badly behaved function and you would be in trouble. But in general, that's going to work. And now we could pause and think about, what does that mean? Well, what that means is that about any equilibrium point, the potential looks like a parabola, right? And in fact, that kind of makes sense. I mean, this looks like a parabola in here, right? This looks like a parabola in here. But if you think about what a parabola is for potential energy, a parabolic potential energy corresponds to a spring, right? And the reason it corresponds to a spring is if you actually ask the question, okay, well, what's the partial of the potential with respect to position? Well, the force is minus the partial of the potential with respect to position. The partial of this with respect to position is 0, because that's just what the value is there. The partial of this with respect to position is, with the negative sign, is going to be minus partial with respect to x squared, evaluated at equilibrium, times x minus xeq, right? So the sort of effective spring constant here is what the curvature of the potential energy is. And so you'll often, when you think about some system being at equilibrium, you should almost always be able to draw a potential energy plot. And then when you look at that potential energy plot, how much curvature there is tells you sort of how strong the spring is that keeps the system in equilibrium. And this kind of approach can be used for everything from thinking about molecules. In fact, on the homework, on the module 4 packet 2, I think I asked you to do an example of this for a sort of classic model for sort of how two atoms interact, to thinking about much more macroscopic level systems where, again, when you're close to equilibrium, it makes sense to think about things acting like a spring, whether it's sort of the tires on your car or, the way that a beam bends in a building. In many, many cases, the restoring forces are linear with displacement. The reason the restoring forces are linear with displacement is because you're disturbing the system a little bit away from equilibrium. And since you're disturbing the system only a little bit away from equilibrium, the potential energy first term that has any functional dependence is a parabolic type of term. Hope that makes sense. If it doesn't make sense, please feel free to talk to me about it. It's kind of a big and interesting idea, but also one that's a little hard to wrap your brain around.